Hello, Mr. Sutton here, bringing you the Pre-Cal Honors 9-4 Extra Practice Number 3 solutions on algebraic limits of piecewise functions. For this problem, I want to find the limit as x approaches -2 for this piecewise function. Now, since -2 is the border value, we have to compare the left and the right side limits. For the left side limit at -2, we're using this less than -2 rule. So -2 plus 2 is going to give us a limit of 0 for that one. And then for the right-sided limit, I have to use the greater than -2 rule. So that automatically just gives us -2 as an output. Since the left side limit and the right side limit do not match, that means the two-sided limit at -2 does not exist. For this problem, we're doing the limit as x approaches 2 for this piecewise function. Now, since 2 is the border value, we have to look at the left and the right-sided limits. For the left-sided limit at 2, we're using this first rule that has x less than 2. So that's going to be 2 over 2 plus 1. Well, that's really just 1 plus 1, which is 2. Now, for the right-sided limit at 2, we're using the after rule, the x greater than 2 rule here. So we've got 2 times 2 minus 2. That's 4 minus 2, which also comes out to 2. So since the left and the right-sided limits agree on 2, that means the overall limit as x approaches 2 also happens to be 2. For this problem, we're trying to find limit as x approaches 1 for this piecewise function. Since 1 is a border value, we compare the left and the right-sided limits at 1. So for the left-sided limit at 1, we're using this first rule with x less than 1. That's going to be -1 minus 2, which comes out to -3. And for the right-sided limit at 1, we're using the after rule, the x greater than 1 rule. So that's -1 squared minus 2 times 1. Well, this is really just -1 minus 2, which is also -3. Since the left and the right limits are both -3, therefore the two-sided limit is also -3. For this problem, we're trying to figure out limit as x approaches -4 for this piecewise function. Since -4 is the border value, we look at the left and the right-sided limits at -4. So for the left side limit at -4, we've got the before rule here, the rule with x less than -4. That's -4 minus 4. Well, this is really +4 minus 4, which comes out to 0. And now we take a look at the right-sided limit at 4. That's going to be using this second rule. So we've got -4 over 2 plus 1/2. That's, let's see here, going to be -3 halves, which does not match 0. So therefore, the two-sided limit does not exist since the left and the right limits do not agree. On this one, I want to figure out the limit as x approaches 4 for this piecewise function. Since 4 is a border value, we look at the left and the right-sided limits. So we're going to have, let's see, left-sided limit at 4. That's going to be the before 4 rule that we're using. So we have -4 plus 7, which comes out to 3. And now for the right-sided limit, we're using the after 4 rule here. So that's -4 over 2 plus 5. Well, that's -2 plus 5, which also comes out to 3. Since the left and the right limits agree, the two-sided limit then will also be +3. On this one, I want to find the limit as x approaches -3 for this piecewise function. Since -3 is coincidentally the border value for this piecewise function, that means we have to try out the left and the right-sided limits on this one to see if they match. So for the left side limit at -3, we're using this first rule because this is the rule for x less than -3. So we're going to have -3 squared minus 4 times -3 minus 3. This is -9 plus 12, which is 3. Minus 3 gives us 0. And now for the right-sided limit at -3, we're using this second rule. So that's going to be -3 minus 3, which comes out to -6. Since the left and the right limits don't match, that means the overall two-sided limit at -3 does not exist. On this problem, I'm trying to find the limit as x approaches 0 for this weird negative fraction absolute sort of function. To make my life a little easier, I'm going to express this whole thing as f of x, just so I can quickly refer to it. And since we have the absolute value, I'm going to turn this into a piecewise function, or rewrite it as that anyway, because it already is really a piecewise function. The behavior of absolute value changes when the things inside absolute value turn from negative to positive or vice versa. So our border value is going to be the kind of the border of those two different rules, which is going to be, in this case, 0. Because when the x values are less than 0, we have to do one thing, versus greater than 0. So we have a rule for x less than 0, a rule for x greater than 0. And by the way, it's going to be whatever x value zeroes out the expression inside the absolute value, which isn't always 0, but in this case it is. So let's say that x is less than 0. Well, let's test out a value like -1. -1 would give me a positive, in which case absolute value doesn't really need to do anything special. So for this rule, I'm just going to get rid of the absolute value and write it like this. Now for this rule down here, if x is greater than 0, well, that would be like, for example, +1. If x is +1, this would come out to a negative inside here, and then absolute value would have to multiply that whole thing by -1 to force it to be positive. So for this rule, I'm going to rewrite this as the negation of this, so positive x in the denominator, or actually we'll do negative x. Yeah, it's the same thing, but whatever. All right, so if I'm finding the two-sided limit, that means I have to find the left and the right-sided limit, which means I'm going to end up plugging 0 into both of these rules. But that's a problem because right now we end up with 0 over 0 if we do that. So let's reduce this a little bit. This top rule can reduce to +1. This bottom rule can reduce to -1. So now the left-sided limit at 0 is going to be +1. Right-sided limit is -1. And since we've shown that these two limits are different, we've shown that the overall two-sided limit at 0 does not exist. On this problem, I'm figuring out the limit as x approaches 3 from the right side for this absolute value fraction function. To make my life a little easier, let me rewrite this whole thing as f of x, and let me also express this as a piecewise function because that's really what absolute value is doing for us. So setting up a piecewise function, my border value is going to be whatever zeroes out the expression inside absolute value, because we have to change our behavior based on whether we're taking the absolute value of a negative or a positive. So the value 3 is going to make things change over, because -3 plus 3 is 0. So I need a rule for x less than 3 and greater than 3. Okay, let's say that x is less than 3. So for example, 2. Well, -2 plus 3 would come out to a positive number. And if you're taking the absolute value of a positive, you don't really need to do anything special. So we're just going to rewrite this without the absolute value for that rule. For the next rule, if x is greater than 3, for example 4, well, -4 plus 3 would be negative. If you're taking the absolute value of a negative, you have to multiply the whole thing by -1 to force it to be positive. So I'm going to rewrite this as negative parentheses, -x plus 3. And before I go ahead and actually try to find the left and the right-sided limits, or either one of those, I'm going to just reduce these a little bit. So this first one reduces to 1. This one down here is going to be -1. And now I didn't really want to find the left and the right-sided limits. We just wanted the right-sided limit at 3. So that's going to be using this rule for x greater than 3. So that's just going to come out to -1. For this problem, I'm trying to find the limit as x approaches 1 from the left side for this piecewise function. Since 1 is a border value, that means we have to choose one of these rules if I'm doing a one-sided limit. Since I'm coming from the left side, I'm going to use the rule where x is less than 1, because that tells us what x is doing up until the point that we get to 1 from the left side. So I'm just going to do 2 times 1 plus 2, which comes out to 4, which is answer choice B. On this problem, I've got a piecewise function defined in both a graph and an actual formula, and we want to know based off of this the limit as x approaches 2 of f of x. So we've got a few things going on. We've got a piecewise function to grapple with, and we also have a limit of a composition of functions. Whenever you're doing composition of functions, you always have to start with the inner function and work your way out. So our first thing we're doing is just finding limit as x approaches 2 of this inner f of x. And we can do that on the graph pretty quickly. As x approaches 2 from the left and the right side, we're approaching a y value of 5. And if you weren't really sure, you could check the left and the right side limits it to, in this piecewise function up here, just plugging in 2 down here, we have 3 halves times 2, which is 3. 8 minus 3 does come out to 5. And you'll see that you get the same thing for that first rule up there. Okay, so we're really doing the limit as x approaches 5 then of this outer f of x function. That's what this is coming out to. So as x approaches 5, well, let's see here. The graph doesn't have x equals 5 shown, but we have a formula for what happens at x equals 5. That's going to be solidly in this last rule here. So we're just going to be doing 8 minus 3 halves times 5. This is really 16 halves minus 15 halves, which is going to come out to 1/2. Choice D.